And then, I know we have an exam next Tuesday. So whatever we finish through today will be on the exam. But whatever we do on Monday will not. Does that make sense? So I do want to finish, definitely I want to finish the aldehyde ketones chapter latest by Monday. I don't think the amount of material right now there is, I don't think we can finish it all today. But we'll see how things go. Is that what you were asking to me?
Yeah, I think that's the
Yeah, I don't think, I don't know, we'll see how things go, but that's, my gut says we probably won't be able to finish it. Any other questions? So far aldehydes and ketones, what we've talked about is their structure, their naming, and their synthesis. So today we'll start looking into their reactions, reactions of aldehydes and ketones. So there's going to be a commonality in all of these reactions because of the structure of aldehydes and ketones. You will see how the mechanisms and the reactions they go through are very, very similar across all different types of reactions. Does anybody remember, is the carbonyl group polar, non-polar?
Polar.
And why is it polar?
Resonant.
So elaborate, that's great, I'm so happy to hear that. Resonance, of course, electronegativity, sure, but also resonance. Because of resonance, where are the poles? Anybody? Partial negative on the oxygen and?
Partial
So
positive.
this bond basically is D sort of, and therefore there's partial positive here in the hybrid. Agreed? Everybody, do you remember us talking about this?
Yes.
So, what is the electronic characteristic of the carbon? Is it electron rich, electron poor?
Electron poor.
So, is it electrophilic, nucleophilic?
Electrophilic.
Who will attack it? Who will attack it? Do you guys agree?
Mm-hmm.
Right? Because it is electron poor. The carbon is electrophilic, which means nucleophile can go there. Agreed?
Mm-hmm.
What about O? Is it electron rich or electron poor?
Electron rich.
Electron rich. So you will see that this will take a proton. And that's kind of a common thing we'll see in all of these reactions. So in all of the reactions that we discuss for aldehydes and ketones, the proton will go to the oxygen and the nucleophile will go to the carbon. So what kind of a reaction is it? So let's say if I am reacting it with something, whatever nucleophilic portion and a hydrogen portion, hydrogen will go where again? To the oxygen.
On the
and
oxygen.
what will happen to this carbon, by the way? What's the hybridization state of the carbon over here?
sp2.
So what will it become once the nucleophile attacks it? What would become the hybridization?
sp3.
sp3. It won't be sp2 anymore. So the hydrogen will go here and the nucleophile will go there. What kind of a reaction is this? Is it addition, elimination, substitution, what?
Eliminate. No, addition
And
across.
what are we adding? Are we adding a nucleophile, electrophile? So all of these reactions, which is what, as I said, the commonality for most of these reactions that we will discuss for aldehydes and ketones would be that they will go through nucleophilic addition. Why addition? Why not substitution? Why addition? Why not substitution? Why isn't the nucleophile just taking the place of one of these guys?
Because the carbon's electron poor.
Okay, but that's not the question though. The question is, okay, when the nucleophile attacks this carbon, which is positive, you're absolutely right about that. My point is, why isn't it just kicking out one of those and taking its place?
Because-
Why not just substitute one of these?
Because they're not living group, right?
Why not?
Because they're bad.
Bad what?
Bad,
That's what
weak
we
bases.
talked about,
Weak-
right?
Strong
Those are
bases.
extremely bad leaving groups. Those are
Strong
R's and
bases.
H's are extremely bad leaving groups. Why are they extremely bad leaving groups?
Weak base.
Good base.
Strong base. Strong bases are bad leaving groups. Weak bases are good leaving groups. These ones, if they leave with a minus charge, R
I got it
minus,
backwards.
H minus are extremely bad leaving groups. Therefore, the reaction cannot kick those out. Therefore, it can't be substitution. It has to be addition reaction. Does everybody understand that? Everybody, yeah? Okay, so what we will see in this chapter when we start looking at the reactions one at a time, what you will see is one of the two ways for these reactions to happen. By the way, when I say this, what I'm meaning is it can either be an aldehyde or a ketone, either an H or an R prime. It can happen in one of two ways. A, if there's a nucleophile, electron rich, where would that go? Where would the nucleophile go? We just talked about it.
On the
2 minutes ago.
electrophilic carbon.
Right? So if that goes to the electrophilic carbon, where do the electrons go?
To the oxygen.
To the oxygen.
So what does that make?
Alcox.
Oh,
It makes an alkoxide ion with an O minus and H or R prime. Basically, sp2 has become sp3. Right? Agreed?
Yes.
And that cannot kick out anything because those are all bad leaving groups. Stops right there. And somewhere proton comes in. So the oxygen O minus, as you've seen actually, and we look at examples, things that you've already seen and learned before, will take the proton and become the product. Make sense, everybody? But please notice the nucleophile went to the carbon, the proton went to the oxygen. So it's an addition reaction. That's one way we'll see these reactions happening. Another way that you can also see the same reaction happen is in presence of an acid. If there is an acid, right now there wasn't an acid, it was just a nucleophile and we had to add an acid later on. On the other hand, if there were an acid, what will happen first?
the oxygen will take the proton first.
We can stop that. Acid-base reactions are always faster than nucleophile, electrophile reactions. So if there's an acid, the first thing that will happen is that the oxygen will take the proton. Oxygen will get protonated. If the oxygen gets protonated, agreed? And then the nucleophile comes in and attacks. The point I'm trying to make is, and give you the same product. The point I'm trying to make is the mechanisms will be one of two different ways. If there is no acid in the system, nucleophile will attack the electrophile and then O minus gets protonated. But if there is an acid in the system, the first thing you've got to do is protonate the oxygen. Then the nucleophile attacks. Make sense, everybody? Good? Okay. So that's general idea of the mechanisms that we will study here. Now, before we actually start looking at specific reactions, I want to also ask you a question. So let's think about aldehydes and ketones. What's an aldehyde again?
RCHO.
So double bond O with an H. Isn't that right?
Mhm.
What's a ketone?
C-double-bond-O to two
R's. Those can be same or different. Agreed? Now, they both have a carbon that is electrophilic. Isn't that right?
Mm-hmm.
They both have a carbon with a delta plus for the same reason, because that's delta plus. Agreed?
Mm-hmm.
Question that I have for you is, which carbon, the aldehyde carbon or the ketone carbon, is more electrophilic? Which carbon, C double bond O carbon, is more electrophilic or more electron poor, basically? Did you say aldehyde carbon?
Yeah.
Why? No, go ahead. Why?
Okay, this might be far off, but
No,
the
not at
ketone,
all.
the ketone has two R groups,
So?
both of which are electron donating.
Good. That's pretty much it. R's are electron donating. Ketones have two R's on them. That means that carbon is getting electron density from both sides. Whereas aldehyde is getting electron density from only one side. Absolutely right. So which carbon is more electrophilic? The
The aldehyde.
Exactly. This carbon is more electrophilic. So if there were ever a choice, and we look at examples, if there were ever a choice, who will react faster with a nucleophile, an aldehyde or a ketone? Who will react faster with a nucleophile?
A ketone.
Want to think about it? Then tell me. Which carbon is more electrophilic, meaning more electron poor? You said aldehyde, isn't that right? So then where would nucleophile want to go faster, to the aldehyde or the ketone? Aldehyde.
Aldehyde.
Absolutely, because it has the more electrophilic carbon. So if there were ever a choice between aldehydes and ketones, aldehydes will react faster with a faster with a nucleophile than a ketone. Does that make sense, everybody? Yes? Everybody okay? Aldehyde carbons are more electrophilic than ketones, therefore nucleophile will prefer to go there than to the ketone if there were a choice. If there is no choice, then of course that doesn't matter. Are we all good? Yes? Questions so far? Okay. So let's start looking at specific examples. Let's start with something we've already seen before, actually a lot. We've also done it in the lab. So reaction with Grignard reagent. Do aldehydes and ketones react with Grignard reagents?
Yes.
Good. So let's start with that because we've already seen it before. Reactions with Grignard reagents. So what happens if an aldehyde or a ketone, again, I'm trying to generalize these because recognizing the pattern actually helps as you're looking at other things. So if you're reacting it with a Grignard, whatever the Grignard is the Grignard bringing in a nucleophile or an acid? What is this supplying to us? The nucleophile or H plus?
Nucleophile.
Okay, so is there H plus in here?
No.
So where would the nucleophile go?
To the electrophilic carbon.
And second step, we add a dilute acid. Isn't that right? We put in an H plus. Where would the H plus go?
Oxygen.
So what's the product? The product is
A secondary alcohol.
depends whether what you're using, but it is an alcohol. Do you all agree?
Alcohol.
So again, depends on, of course, what we started with, but we'll get an alcohol. So we've done this reaction a lot. We've looked at mechanisms. We've done it in the lab. Yes.
Why do we have H and then R1? Like, wouldn't it?
It's either an aldehyde or a ketone.
Oh, okay, yeah.
So
I was
I'm
like,
just
how is
giving a
that
general
an aldehyde or ketone? Yeah, okay.
It's either one of those.
Got it.
I'm generally giving a general representation. So for example, if we are, let's try, excuse me, this is the one you did in the lab last quarter. You took benzophenone, you reacted it with phenyl magnesium bromide, and followed by a second step. I can't write. Did I write that correctly?
Forgot steps 1 and 2.
And why is that so important?
Because the Grignard would react would get a proton from the acid.
So Grignard and the protic source cannot be together. Cannot have them together. Otherwise you won't get what you're looking for. Can someone tell me what is the product?
Triphenyl methanol.
Triphenyl methanol is what I heard. Okay, let's write a mechanism quickly. So what's the first step?
Grignard attacks the electrophilic carbon.
Yeah, because there's no acid there, right? First step has no acid, so you can't protonate the oxygen. So absolutely, the nucleophile, which is coming from the Grignard, goes to the electrophilic carbon, creates an alkoxide. Stops right there. Why does this step stop right here? Why does this step not go further?
Because there's no source of proton.
Okay, good. One reason there's no source of proton. Why else? Okay, but why can't it just, the negative charge fall back and kick out one of those? Because it had
No resonance.
no leaving group.
No good
No
leaving
leaving
groups.
group, nothing more for it to do. Stops right there. This is where esters are different from aldehydes, ketones. This is where acid halides are different from aldehydes and ketones, as we will see in next chapter.
Also
So
be-
we have to recognize that there's nothing more for this to do than to take a proton, but it has to wait till you give it protons because it doesn't have any. But none of these are good. These are very bad leaving groups. What were you saying, Mark?
Yeah, well, I guess for the same reason, no resonance.
Yeah, I mean, that's not allylic or in
Yeah.
the allylic position also.
And because,
And resonance is not a chemical, it's a phenomena. That's not, right, that's not a, how do I say this? It's not like this is becoming the resonance structure,
It's a-
right?
uh-huh.
It's there.
yeah.
So what's going to be the next step, anybody?
The oxygen takes a proton.
So then you bring in the proton, make the product. Have we seen this before?
Yes.
Everybody?
Yes.
Any questions? Do we need to write this mechanism more, or you know this mechanism because we've done it so many
I think it's
times?
good.
Perfect. Cool. So this reaction we already know. By the way, where does a Grignard come from?
You react a
Magnesium
Okay,
benzene.
we need
with a
magnesium.
halogen.
Where? What?
Br2.
No.
Wait.
What gives us Grignard?
Alkyl halide?
An alkyl
Alkyl
halide.
halide.
Whatever that is. And of course, where does the alkyl halide comes from? Well, it depends on where you're coming from. Alcohols can be converted into alkyl halides. Alkenes can be converted into alkyl halides. Alkanes can be converted into alkyl halides. You have all those choices. Is that okay, everybody? Yeah? Questions about this one? Okay, cool. So that's one reaction. Let's look at another reaction and notice the similarities. Notice the patterns in all of these mechanisms. The next one is hydrate formation. Making a hydrate. What is a hydrate again? Anybody remember from last class? Say that again.
Double diol?
It's a geminal diol. By the way, hydrate formation, also known as hydration, I can call this. Mark, could you do me a favor?
Yes.
Thank you so much. Also, you could call this a hydration reaction. What are we adding? If we are doing a hydration reaction, what are we adding across the pi bond? Anybody? Louder?
We're adding in
Water.
Water, exactly. We are adding water. Oh, I see. So, aldehydes or ketones. Of course, aldehydes react faster than ketones, as we just discussed. Aldehydes are more electrophilic than ketones, so they will react faster. So both of them can be converted into a hydrate. How do I write this? Okay, I'm going to show you. So what are we adding? We are adding water across the pi bond. If you're going to add HOH across the pi bond, what will it become? This becomes a hydrate, which is a geminal diol. Isn't that right? This reaction can be done in two ways. Adding water to an aldehyde or a ketone can be done in two different ways. Either with acid catalyst or a base catalyst. So this hydration reaction is catalyzed. It can be catalyzed either by an acid or by a base. And these reactions are also reversible. They can easily go back. So there's generally an equilibrium between what we call the keto form, even though it could be an aldehyde, it's the keto form or the hydrate form. There is always going to be an equilibrium in physiological systems, in biochemical systems, because you're dealing with aqueous environments in those cases. But in general, there are exceptions, but in general, keto form is the more stable of the two, in general. So when there is an equilibrium between the keto form and the hydrate form, it is the keto form that exists in greater concentration than the hydrate form, in general. Exceptions are there. Does that make sense, everybody, so far? Okay, let's look at some examples and then we'll write mechanisms to understand how, why, so on and so forth. So let's start with 2-butanone as an example. Please go ahead, let's draw the structure of 2-butanone. What does 2-butanone or butane 2-on look like? Agreed? Product with, what would the product be? Or it can also, of course, be base catalyzed, which means you've got a dilute base. What would the product be? What are we adding across the pi bond?
Water.
So the product will be, once again, sp2 carbon is becoming sp3 hybridized.
Geminal.
OH.
A geminal
Make
dye.
sense? Everybody, let's write a mechanism for both the acid catalyzed process and the base catalyzed process. So let's start with the acid catalyzed process first, and let's write the steps for the mechanism. What would be step number 1 in your opinion?
Will protonate.
Say that again, please, Mark.
Protonate.
What will protonate?
The O.
Oxygen. Because there's an acid. So if there's an acid, the first thing you do is protonate the oxygen. Period. Okay. Oxygen gets protonated. Now what? What will happen after that?
Water would attack.
Because water is the nucleophile, right? Water is the nucleophile, so the water will attack the electrophilic carbon. After the oxygen is protonated, the nucleophile will attack the electrophile. Make sense, everybody? What will that create?
The alkoxide.
No, not here. You can't have an alkoxide in an acidic environment. You'll get that.
Oh,
Follow
yeah.
through the process.
Yeah. It's still
Agreed? Everybody okay?
Mhm.
What do you think needs to happen next?
The oxygen for the OH2 gives away a proton.
So you mean another water molecule will come and take the proton? Is that what you're saying? Or you're saying
Yeah.
this OH will take that proton? What are you referring?
Oh, water would take a
Okay.
proton.
Cool, absolutely right. I'm not going to write it that way because when you're writing catalyst, whatever form you use the catalyst in, you show it in the same way being recreated. So since I started with H+, I should show H+. If you started with H3O+ instead, then you will show H3O+ being created. Does that make sense?
Yes, for catalyst.
Right? So because I did that, of course, please remember this is nothing but H3O+. That's exactly what it is. So it depends on how you prefer to write it. But since I started with H+, I'm going to create an H+ and show how it's catalytic in the acid. Does that make sense? So once again, is it wrong to write H3O+? No.
No.
It's all about being consistent to show the catalyst being created like the way you used it. That's all. Make sense, everyone? Okay. What about the base catalyzed process? So if you're writing the mechanism for the base catalyzed hydration reaction, let's see how that's going to go. So what do you think will be the first step?
The negative goes into the C.
Negative of what?
Oh,
Alcohol.
There's no alcohol.
Oh, hydroxide.
Hydroxide. Hydroxide, there's no acid here, so no protonation. Nucleophile attacks the electrophile.
Now we have an alcox.
Now we have an alkoxide. Absolutely. So we now have O minus. So what is this O minus? What do you think should be the next step?
It receives a proton?
From?
Water.
Exactly. And if it receives a proton from water, what is it going to create? If it takes the proton from H2O, what happens to those electrons?
Those electrons will go back to the oxygen.
So what is recreated?
Hydroxide.
Exactly. Catalyst used, catalyst created. You got to show that in your mechanism. So again, please notice the pattern here. Because there was an acid, oxygen protonated first, then nucleophile attacked. When there is no acid, nucleophile attacks, then gets protonated. Does that make sense, everybody? Yes? Sure?
Yep.
Okay, cool. Let's do it again.
Why?
Yes?
No, never mind.
What?
Why in this case? I mean, I know because it's a pro, and I know that's the way it is. But
No, what?
but I would probably, in a test, get confusing. When I get to the HO,
Yes.
I probably make it a living room group.
But then aren't you just going back?
Uh-huh.
Yes, it's reversible. You're right, absolutely. All of these steps are reversible. So if that's a leaving group, it just goes back and then back.
Mm-hmm.
But we are trying to write a mechanism for the forward.
Okay.
If you have to write the mechanism for the reverse, then you'll of course have to think in that way. Does that make sense?
Mm-hmm.
Okay, how about benzaldehyde? Benzaldehyde. Again, we'll write both to practice. It's all about practice. So we are trying to write the mechanism for the forward direction. So please give me, maybe this time I'm going to write it as hydronium or aqueous. Different ways of writing the same things. Can you tell me what the product will be and then write mechanism for both? So what will be the product?
A geminal diol.
And where?
On the carbon attached to the benzene.
So the aldehyde carbon, right? It's this carbon right there. So, of course, there's a hydrogen too. Agreed? Let's write the mechanisms. How about the acid catalyzed one? First step, first step.
Oxygen takes a proton.
Is there any difference in H plus and H3O plus? Are they any different from each other? Not at all. They're exactly the same things. So however you write, it's a matter of preference. Absolutely, the oxygen takes a proton from hydronium. What does it become?
OH2
OH2 positive charge. That's okay. What will this become?
H2O.
Agreed? Protonated the oxygen. Now what should be the next step?
Water attacks.
The electrophile. Nucleophile attacks the electrophile. Right?
Mm-hmm.
What would that become? Am I right? What does this need to do?
give away a proton.
Now how would I need to show that? Should I just show proton leaving or something else?
Water takes a proton.
Because we started with hydronium, we need to show hydronium. Oh, wrong hydrogen. One of those, right? If you started with hydronium, you recreate hydronium. If you started with H plus, you recreate H plus to show that the catalytic property, but it means the same thing. Everybody okay? Okay, let's do the base catalyzed one. So step number 1. Come on guys, it's on the board.
Yeah, I'm just writing.
Hydroxide attacks the electrophilic carbon.
And makes, in this case, a,
Alkoxide.
although I won't call it strictly an alkoxide because there's an OH here, but I understand what you're referring to. What should be the next step?
The negatively charged.
Where did the H2O come from?
It's aqueous.
Exactly. Please recognize there are different ways of writing exactly the same thing. Exactly. So, yeah, go ahead, please. Ali, what were you saying?
The negatively charged oxygen will get a proton from the water.
Exactly. And these electrons,
Go to the oxygen.
they recreate hydroxide ion, and then you have your hydrate. Does that make sense, everybody? Is there anyone who doesn't understand any part of this? Everybody gets it? Cool. If you get the forward direction, can you write for me the mechanism for the reverse reaction? Meaning a hydrate being hydrolyzed back to the keto form. So let me give you an example.